Single crystal elastic constants define the property of a material that undergoes stress, deforms, and recovers to its original shape after the stress ceases. Single crystal elastic constants determine how to use a material with guaranteed structural stability, and they constitute the basis for physical modeling and materials design. So it's very fundamental to know single crystal elastic constants of any given material. Then the question comes out naturally: how do people measure single crystal elastic constants? As most materials exist in the form of polycrystals, people can either cut a polycrystal to get single crystals for measurements, or carefully grow a single crystal from atoms. However, both methods are complicated in preparation, ineffective in time and cost, and even inapplicable for many materials. Based on a report from National Science and Technology Council, there are 116,000 different solid crystals, but only 1% of those crystals have experimental values of single crystal elastic constants. That shows a huge gap between what we know and what we need to know. My research is to break this limit. We have developed a new method that enables measuring single crystal elastic constants directly from polycrystals. The principle is like this. We use a laser to generate and detect surface acoustic waves on the sample surface. The surface acoustic waves is on the surface of local single grains in a polycrystalline sample. Surface acoustic waves on a sample surface is like ripples on the water surface. Its velocity is highly related to single crystal elastic constants. On the other hand, we have developed a model that can predict surface acoustic wave velocity along any direction at any elastic constants. Therefore, we can extract single crystal elastic constants by using our model to fit the experimental measurements. Our method proves accurate and reliable and brings benefits to industry and academia. So far, we have been collaborating with General Electric to measure a material used in jet engine blades, collaborating with Taiwan National University to measure a material used in three-dimensional interpretive circuits, and collaborating with Northeastern University to measure a material used in magnetic refrigerators. That's the next generation of magnetic refrigerators. So probably there is a reform in your kitchen next time. So we hope this method can get extensive use and benefit science and engineering in many more ways. Thank you.